Hi everyone, and welcome to the fourth lecture in this mini course of Gopakumar-Vafa Invariants. Today, Yukinobu will talk about Donaldson-Thomas theory. Please go ahead.
Yeah, thank you very much. So today I will talk about Donaldson-Thomas theory using the preliminary in the previous lectures. So this is some invariant on Calabia's threefold. So let's recall that Calabia's threefold is a complex three-dimensional variety which has the trivial canonical class. And also let's take V that is a numerical class that corresponds to the Chern character of the sheaves, which I want to consider. But then in this setting, so there is also we have to also choose some polarization H. So yeah, I will explain later that H is some amplitude divisor. So this corresponds to the choice of stability conditions. So then from this data we can define some invariant. And also under some assumption, we can define the invariant, which virtually counts H stable sheaves. So stability condition was defined in the previous lecture. And it virtually counts stable sheaves with Chern character V, and this is called Donaldson-Thomas invariant. And there are also several generalizations and also several variants of this construction, which I will also explain later. Anyway, so this is holomorphic version of so-called cast invariant. So there are some similar invariants on near 3 manifolds, and this is holomorphic analog of this one. And also on algebraic surfaces, there is also so-called Donaldson invariants, which counts also stable vector boundaries on algebraic surfaces. This is also regarded as a kind of higher dimensional generalization. And this theory is very important and interesting in several branches of mathematics, like not only algebraic geometry or mathematical physics, but it also interesting in representation theory, cluster algebras, combinatorics, and so on. So the main purpose is to explain the relationship between the rank 1 Donaldson-Thomas theory. So basically, the Donaldson-Thomas theory counts sheaves, so it may not be necessarily directly count curves. But if you only consider rank 1 theory, then it counts curves. So this is a curve counting theory. And there are several curve counting theories like global fitting theory and Gopakumar-Vafa theory. And this correspondence is very established theory. And the purpose of this lecture is to explain another theory, Gopakumar-Vafa theory, which has the relationship of these theories. And this relationship is still mysterious in many cases. Anyway, so here is a rough idea about Donaldson-Thomas theory. So let's consider moduli space of stable sheaves, which we discussed in the last lecture. So then let's recall that. So we know some local description of this moduli space, that is locally at each point. So the tangent space of this moduli space is given by x1. So this is the tangent space. And x2 plays a role of the obstruction space. So the first order deformation of this sheaf is governed by this x1. But there are some obstruction class on here, so that this obstruction vanishes if and only if this sheaf is further deformed to higher order. And this information can be packaged into this so-called Kranich map that at least in the analytic neighborhood of the origin of this x1 EE, so there is some complex analytic map from here to here, such that this moduli space is cut out by this function. Now here is a point about considering Calabia's effort, because the point of Calabia's effort is that the obstruction space and the tangent space are dual to each other. So this is forward from the Series duality and Calabia's three condition. So let's recall that for simplicity, if you assume that it is a vector bundle, this left-hand side is given by the H2 of form of EE. But the seriality is said that this is equal to H1 of home E dual tensor omega x, but omega x is trivial, so we can ignore that. So then this is nothing but the dual of the x1. So this is the important point of considering Donaldson-Thomas theory. This is also defined point from the clone-fitness theory. And in particular, this means that the tangent space and the obstruction space have the same dimension. This means that this modular space of sheaves on Calabian seafood is virtually regarded as zero-dimensional sheave. Virtual means that so the tangent space is x1, but we have some obstruction space. So for example, if this kappa is a very somehow generic section, so that the tail locus has a correct codimension, then it must be zero-dimensional because this is the difference of the dimensions of the obstruction, tangent and obstructions. However, in most of the cases, this kappa is not such a generic section. So more precisely, this is not a regular section, so that the zero locus of this function may not be zero-dimensional. In fact, in general, this dimension is positive. So in that case, usually that happens in considering animated geometry. So the general idea is to construct a virtual fundamental class, which is the correct dimension. And in this case, we want to consider zero-dimensional virtual fundamental class. So yes, first I explain about virtual fundamental class. So in general, let's consider the following situation. So this is more general than the previous one. Let's consider some smooth scheme U, and also some vector band V on U, and with section S. So the section is here. And then let's take the zero locus of this section, which I denote by M. So this is M equals 0. So then, starting from this data, we can define this map diagram of complexes. That is, let I is the ideal sheaf of M. So this is nothing but the equation given by S, generated by the equation given by S. So then we have the following morphism of complexes. So this E dot is a two-term complex of vector bundles. That is, because I assume U is smooth, so this is vector bundles. These are vector bundles. And so there is a canonical map from here to here, and given by this section S. And there is also a canonical map from here to here. And then as a consequence, we have this commutative diagram. So this gives the morphism of the complexes. So this E dot is nothing but this one, and this one is this one. The bottom one is called truncated cotangent complex. That is, so a priori, so this is defined by taking locally embedding M into some scheme U and write it as some zero locus of some section. But this is defined somewhat intrinsically. So this is well defined and independent of the choice of this embedding. And then there is such a map. And this map governs the so-called deformation obstruction theory, at least locally. And in that situation, if the section is regular, this means that if the codimension of S is the same as the rank of the vector bundle V, then one can show that yes. So anyway, so the regular section means that the closed subscheme has codimension R. So this is the definition of the regular section. And in this case, if you take the push forward of the usual fundamental class of M to here, then this class equals to the usual Euler class. So this is more or less the definition of the Euler class. But in general, so there is also a class, not on U, but on M. So this is called the localized Euler class. This lies in some more homology of M. Well, more algebraically, this can be also taken in the child group of of M, such that its push forward equals to the usual Euler class. So the point is that the usual Euler class lives in this ambient space, but it can be localized to here. So it is in fact coming from some class on here. And this is the prototype of the so-called virtual fundamental class. And this localized Euler class can be also constructed quite explicitly. So let's I be the ideal sheaf of M. Then we have the following normal cone over M. That is, this is a spectrum of the direct sum of this the graded algebra over M. So in fact, if M is non-singular, if M is non-singular, then this is nothing but the total space of the normal bundle. But in general, if M is singular, this is not a bundle, and this is just a cone. But nevertheless, so this one, so this normal cone is affine over M, and which is of pure dimension U. And in fact, this is a closed subset of we have the vector bundle V, and it is restricted to the vector bundle over M, and this is in fact closed. So this is this follows from the surjection of this diagram. So then now this is has dimension U, and this is rank we have the vector bundle of rank V. And then we have also the zero section of this vector bundle. So then we can take the pullback of this cone by this zero section. So there is some sort of pullback in this situation called Gaussian pullback, and so this Gaussian pullback gives the correct dimension of this localized Euler class. In fact, so this has the dimension U, and by this pullback, we have the dimension is dimension U minus dimension V. So it lives in the correct dimension. So it is H twice of the virtual dimension. So this gives the local construction of the so-called virtual fundamental class. So the idea of the construction of the virtual class is somehow globalization of this picture. So in general, so such a localized Euler class can be globalized using the notion of perfect obstruction theory. So this notion is due to Berendt and Fantecchi. So in general, for a given scheme M, a perfect obstruction theory is, so this is a morphism in the derived category of coherent sheaves on M. This is phi e to this cotangent complex. So in the previous slide, so if M is in fact given by some zero section of some vector bundle, we could explicitly construct such data using this section. But in general, so we don't know whether this M is given by a zero section of some vector bundle. And nevertheless, so in severe modular problem, we can construct such perfect obstruction theory. So by definition, this is locally isomorphic to a two-term complex. That is locally, so this is quasi-isomorphic to the two-term complex. So what I say isomorphism means that, so isomo in derived category, so I should say this is quasi-isomorphic. So locally isomorphic to this kind of two-term complex. And the property is that the induced map on zeroth cohomology is isomorphism, and the -1 cohomology is surjective. So in fact, such a perfect obstruction theory can be shown to be equivalent to this kind of diagram, which was appeared in the before. So this is an example of perfect obstruction theory. And in fact, every perfect obstruction theory can be locally of this form. In fact, this map is surjective, so the H inverse phi is in fact surjective, and H0 phi is isomorphism because the zeroth term is in fact same. And indeed, so this one corresponds to the tangent space of the moduli space. In fact, this is because this is isomorphism. So this is in fact isomorphic to the tangent space of the moduli space because of this isomorphism. And this one corresponds to the obstruction space. And the point is that for scheme M with perfect obstruction theory, there is associated partial fundamental class. The local setting, if this perfect obstruction theory is given by this, like V dual to n. So in this case, we can consider the localized Euler class, as I explained. And so this is the partial fundamental class. But the point is that it can be also further globalized. So it gives the global version of the partial fundamental class. So there are also several constructions of this partial fundamental class. For example, there is also a way to construct virtual class using derived algebraic geometry. For example, in several contexts of moduli theory, like Gromov-Witten theory, Donaldson-Thomas theory, so the moduli space is not only a scheme, but like derived scheme. So it has some derived structures. So then using these derived structures, it is also possible to construct a virtual fundamental class. But the point of this virtual class is that, so this was produced before the derived algebraic geometry developed so much. So this, roughly speaking, so the perfect obstruction theory corresponds to the tangent space of the derived moduli space. So in order to get a partial fundamental class, it is enough to consider the tangent space of the derived moduli space. This is tangent of the derived moduli space. And also, technically, it is also more difficult to construct a virtual structures on the moduli problem. But anyway, so in many contexts of the moduli theory, we can construct perfect obstruction theory and also construct a virtual class. The virtual dimension is, so this is the rank of the perfect obstruction theory. So perfect obstruction theory was this one. And the rank of E is given by, so if E is a complex of this form, then this is the difference of the rank in that case. But in the case of moduli of Stevenson-Calabian seafold, the obstruction theory is more special. That is, it has some symmetric property. So as I explained, in the case of Calabian seafold, the tangent space and the obstruction space are dual to each other by the theory duality and Calabian condition. And such obstruction theory is also formulated as so-called symmetric perfect obstruction theory. So by definition, perfect obstruction theory is called symmetric if there is this isomorphism. So in this context, this E corresponds to like the x1 E dual and x2 E dual. If you take the cohomology of E, then we may get something like this. So then this is in fact dual to each other, but up to some shift because of this theory duality. So this is also explained in terms of derived algebraic geometry. So there is so-called the minus some sheeted symplectic structure, which is some pairing between the tangent complex, but shifted by one. So this is also somehow shadow of the so-called minus some sheeted symplectic structure. And this is but the data of the minus one sheeted symplectic structure is something more, and that is used to define the DT invariants. Anyway, so in order to define the numerical DT invariant, it is enough to consider the symmetric perfect obstruction theory. So let them be the moduli space, and let's assume that this is a fine moduli space. So let's recall that fine moduli space is that it represents the factor of, so this is representative of the factor. So in particular, so fine means that there is no strictly semi-stable sheaves. And also there is no, and also there is a universal family. So this condition is important in defining DT invariant using virtual fundamental class. Because of the first property, the moduli space of stable shifts is in fact proper. In this case, it is in fact projective. So universal, the existence of the universal family is this is something technical and not so much essential. But anyway, so this is good if there is. So then there is a symmetric perfect obstruction theory on this moduli space M, where this is explicitly constructed in this way. So here, this U is a universal sheaf, and I take the R home in the derived category, and then take push forward to M, shift by one, and take dual. And zero means that taking the traceless part. The traceless part is that so there is a map from R home into gamma on X by taking trace. And in fact, this map splits in many cases. For example, if we have a positive rank, this map splits so that it decomposes into the direct sum of the trace-free part and also this part. Roughly speaking, this means that if you don't take this one, we also have the contribution of the home and X3 EE. But if E is stable, then both of are one-dimensional. And it coincides with the H0 or X, and this one corresponds to H3 or X. So by taking the traceless part, we can ignore this part. So it also has some effect if the Calabian fold has a non-trivial H1. In this case, we also keep the deformation of the sheaf keep the deformation so that the foot determinant also deforms. So this also gives the meaning that we also fix the determinant of the sheaf. But in many cases, we assume that H1 or X equals 0. So in that case, this traceless part only implies that we only ignore the home and X3. And from this construction, the first, the zeros and -1 cohomology of this one is the dual of X1 and dual of X2. So by taking dual, we get the tangent space X1 and the obstruction space X2. So this is how the perfect obstruction theory can be constructed on this moduli space. And also this is symmetric because of this Calabian condition. So then from what I had explained so far, so there is associated zero-dimensional partial fundamental class. And since I assumed M is fine, it is a projective scheme. So then by taking the degree of this zero-dimensional partial class, I get the invariant. So this is the original Donaldson-Thomas invariant. And in fact, this is invariant under deformation to the complex structure of X. So this is a general phenomena which happens for enumerative invariants defined using the virtual fundamental class. So let me give some examples. So usually, so the dimension of the modular space is positive dimensional, but there might be some cases that in fact this becomes zero dimensional. So this happens when the modular space is spectrum of Artinian ring. So although this is zero dimensional, but it has some non-trivial scheme structure. Yeah, for example, it may happen that M is like spectrum of Ct over Tn, I think. So in this case, the usual fundamental class is the virtual fundamental class. And in this case, this equals to the just the dimension of this R. Because this is Artinian algebra, so this is finite dimensional vector space. So its dimension, in fact, gives the dt invariant. As another example, so this is somehow extreme case. Let's assume that M is in fact smooth, but may have some positive dimension. So then in this case, we can see that the symmetric perfect obstruction theory is in fact given this way. Yes, at least, yeah, I should say, so this is true, at least locally. But yeah, let's assume that this one is also true, yeah, globally. So then the Donaldson-Thomas invariant is given by the integration of this dual of this one. So this one now corresponds to the obstruction class, obstruction space. More precisely, its dual is obstruction space. And in that case, we take the integration of its Euler class. So this is nothing but the Euler number of M up to sign. So in some sense, so in this case, you see that the Donaldson-Thomas invariant is closely related to the topological Euler number of the modular space. So this happens because by the Calabi-Yossi condition, the tangent and obstruction spaces are dual to each other. And this is very special in the Donaldson-Thomas theory. So for this one, this property is not true for chromophyton theory. So in this way, we have some close relationship between the Donaldson-Thomas invariant and the Euler characteristic, usual Euler characteristic of the modular space. In fact, so we can some more precise relationship between Donaldson-Thomas invariant and Euler characteristic using the so-called parent functions. The dt invariant can be also obtained by certain Euler numbers, but are weighted by some function. So it is described by Milnor fibers. So in general, let be a complex manifold, and f is a holomorphic function on it. So then we can define the so-called Milnor fiber of this function f. And at this point, P, it is given in this way. So this is, we have point P, and we take some neighborhood. And we have the function f. And that I take some sort of nearby fiber of this one, something like this. And this is Fp, and this is option. And I fix some norm in the neighborhood of this P. So this Milnor fiber is, so this is closely related to the critical locus of this function f. So this critical locus is, the notion of the critical locus is very important in the Donaldson-Thomas theory. So for a given function f, we have the so-called critical locus. So this is defined to be the zero locus of the one form. Another way to say is that if you are given coordinate x1 to xn, so that the function is given this way. So then critical locus is given by this, the locus of this, the deviations. So then we have the so-called the notion of variant function. For any complex scheme M of a finite type, there is a so-called canonical constructive function, which is denoted by chi b, satisfying the following conditions. For a point x, let's assume that there is some analytic open subset such that this M is given by critical locus for some function on some complex manifold V. So then in this case, this variant function is given by the Euler number using the Euler number of the Mueller fiber of F. So given this function F, so there was a so-called Mueller fiber that is something like a nearby fiber of this function F. Then using this Mueller fiber, the variant function is described in this way. In fact, for the modular space of sheaves on Calabia's threefold, so this M is always locally little in this way. So this is given by some critical locus of some function. So it is enough to consider the Mueller fiber to compute this variant function. So then the relationship between this function and the Donaldson-Thomas invariant is that if M is proper and also admits a symmetric perfect obstruction theory, of course, this is satisfied when M is a fine modular space of stable sheaves on Calabia's threefolds. Then the degree of this virtual fundamental class equals to the weighted Euler characteristic of the variant function. So this is defined as in this way. So this is something similar to the Euler characteristic, but weighted by the value of the variant function. So in particular, when the modular space is smooth, then this chi b is in fact a locally constant function. It is just the -1 power of the dimension of the modular space. So then using this description, we can recover the previous computation using the Euler class of the obstruction space. And in general, the modular space has singularities. So this chi b function, variant function, keeps track of the singularities of the modular spaces. So using this the variant function, we can also describe this degree of the virtual fundamental class using this function. So again, so this is also a special feature of the Donaldson-Thomas invariant, and this is not available for other enumerative invariants. So here are some examples of variant functions. Let there be a function given by f equals to power of t. Then, of course, the Mueller fiber is just n plus 1 point, because this is just solving the equation that n plus 1 equals something epsilon. So there are n plus 1 distinct point. And also in this case, the critical locus is this one. So this is given by just the derivation of this function, t. And in this case, of course, there is only 1 point. And the value of the variant function at this point is, if we apply the previous formula, then this is given in this way. So this is the Euler number of the Mueller fiber, and this is the -1 power of the ambient space. And so this gives just n. So then it also, sorry, maybe it has mistake. So this is just -1 power. So this is -1 product minus n. So it becomes just n. So then again, this one equals to the dimension of this link. Another example, let's take f to be this function. So then the critical locus is given in this way. So this is given by derivation by x and y. So by taking the derivation of y, I get this one. By taking the derivation by x, I get this one. And in this case, so the Mueller fiber is shown to have Euler number 0. So there, so yes, one can easily see that because there are some non-trivial free S1 action on the Mueller fiber, which makes this Euler number to be 0. So then this is also easy to compute the bend function. So for at the origin, this is just 1 using the previous formula. And the geometry of this critical locus is that, so theoretically this is the same as xy equals 0. But there are some non-trivial scheme structure on here, on the origin. In fact, this scheme is non-reduced at the origin. So except origin, so this is smooth. So in that case, this is just a constant -1. But at this point, this is singular. And in fact, so it is also known that if the schema admits a symmetric or structural theory, so that applies for the critical locus of some function. So then this is if this is not smooth, then it cannot be locally complete intersection. So this means that there is no critical locus something like this. And it is essentially important that we have some non-trivial, non-reduced scheme structure at the singular point. And as I said, it is always true that the moduli space of stable shifts on Caviar C4 is always written by critical locus. So this is due to Joyce and Son. Let X be Caviar C4 and take M to be the moduli space of stable shifts. So then we recall that there is so-called Kranich map. This is an analytic function. And in fact, this analytic function is given by the one form associated with this subfunction f. So you can regard this x1 as the total space of the cotangent bundle. So this kappa is regarded as a section of this cotangent bundle. And this section is in fact given by the Drum differentiable sum function. So that its zero locus is nothing but the critical locus of f. This theorem was also proven by Joyson using gauge theory, but now there is also other proof using derived algebraic geometry and also shielded symplectic structures. So I give some another example. So this example is due to in the paper by Thomas. So let X be a Calabian C4 given by 3 divisor. So this is the section of line bundle given by the line bundle given by like P1 star or 3 tensor P2 star or 3. And this is in fact Calabian C4. And for some choice of section, there is such Calabian C4 such that the this first projection gives elliptic vibration of X. And for some choice of X, so there is a singular fiber of this form, so X square equals 0 and Y equals 0. So there is some non-reduced fiber and also reduced fiber, and it contains P1 of C as one of the non-reduced fibers. So then he computes the moduli space of stable sheaves, which contains this structure sheaf. And in fact, he showed that this is a spectrum of this Artinian link. And in fact, this is the critical locus of this function z cube plus w cube over C2. So then it is also easy to compute the lunar fiber. So, and the DT invariant is nothing but the 4. This can be also shown just by computing the dimension of this Artinian algebra. So this is, in fact, C plus CT plus CW plus. So this is the definition and example of DT invariant. And now I'm going to explain about the generalized DT invariant. So this is another very important story in DT theory. So far, the DT invariants are defined when the modular space of stable shift is fine. So so this means that there is no strict semi-stables, and also there is a universal family. And the point that there is no semi-stable shift implies that every point on here has a trivial automatism group. That is, automatism group is just the one-dimensional torus. And by taking the traces part, we can ignore these contributions. But if there is a semi-stable shift which is not stable, then automatic group is bigger than this one. For example, if E is the direct sum of stable shifts, then the automatic group is like GLN or something like that. So if the modular space is fine, then this condition holds, but it is natural and important to consider such a case. For example, we want to consider invariant counting shifts, something like the direct sum of the structure shift. So such a theory is not included in the previous definition of the DT invariant. However, the construction is not straightforward if there are some strictly semi-stable shifts. If this inclusion is strict, then we have several issues. The first issue is that, okay, so we have still the good modular space with stable shifts, but this is not proper. So still you can define the virtual fundamental class, which is zero-dimensional. But if this is not proper, then it does not make sense to take its degree. We cannot take the push forward of the child group of the zero cycle to the point. So then we can try to consider, instead of this one, we can consider the good modular space of semi-stable shifts. Now this is projective. So this gives a compactification of this modular space of stable shifts. However, so the natural perfect obstruction theory does not extend to here. So this is basically because by getting rid of the traces part, we still have the contribution of the x0 and x3 because they are not one-dimensional. So it does not admit natural perfect obstruction theory. So then we can also consider another way using varied functions. The varied function one may make sense. And we can try to integrate its varied functions. However, so there are examples that it is not the correct one. That is, by defining these invariant, we want them to be invariant under deformations of complex structures. But the integration of the varied functions over these modular spaces do not behave well. So this is basically because, so this y is not necessarily given by critical locus. So this y is given by critical locus, but this is not. So then the issue that this is not given by critical locus is that because this is just a good modular space, not a modular stack. So then instead, let's consider modular stack. So then we can show that this is again given by critical locus locally. And also the varied function on it makes sense to consider. However, the issue is that the Euler characteristic of outing stacks do not make sense in general. So this is now outing stack. For example, if you consider the cohomology theory of outing stack, for example, if there is some group action on X, and X is the quotient stack of this one, then this is the equivalent cohomology. But usually, so this is not finite dimensional. So it does not make sense to consider its Euler characteristic. So there are similar issues, but the last one is the way to resolve these issues. So the point is that the naive Euler characteristic does not make sense, but still there is a way to make sense of the Euler characteristic of the outing stack. So remember, Joyce also defined the so-called generalized DT invariant, which counts semi-stable sheets with given Chern character, and it coincides with the previous one when the moduli space is fine moduli space. Roughly speaking, instead of considering the moduli stack, the point is that they take the logarithm of this moduli stack in some way. So that is what I'm going to explain a little bit. So the point is, by taking the logarithm of this moduli stack in some way, this stack is virtually regarded as some sort of scheme rather than stack. So then it makes sense to consider the integration of the Bennett function or weighted Euler characteristic. And this log is taken in terms using the so-called motivic Hoover algebra, which I'm going to explain. And by regarding this moduli stack as some element of this motivic Hoover algebra. Now I'm going to explain about the motivic Hoover algebra. It is defined to be certain quadratic group of stacks over the stack of coherent shifts. This algebra is defined using the modular stack of exact sequences of coherent shifts. So roughly speaking, this algebra structure keeps track of the Abia category structure of the category of coherent shifts. And there are several formalism of defining it. And here in this lecture, I use the formalism developed by Bridgeland. First, I give the definition of quadratic group of stacks. Let S be an outing stack of finite type over complex numbers, and assume that it has only affine stabilizer groups. That is, for any point, geometric point, assume that the automated group of X is affine. So this is true in the usual context in DT theory. For example, if we consider modular stack of objects of coherent sheaves or derived categories, then this condition is always satisfied. So then I define this stack, this group. So this is a group generated by, in fact, this is a Q vector space generated by this symbol X to S, where X is outing stack over S, and also with fine stabilizers. Yes, so I think I forgot to write outing stack for finite type. The fine stabilizers and satisfying some relations. So this is reasonable conditions, which is similar to the one which appeared in the quadratic group of varieties. For example, for the disjoint union, so I take the sum of these classes. And also for if there is equivalence of the groupoid for each geometric point, so then it must have the same class. The last one is a bit tricky, that if there are some Zariski local trivia vibrations, Zariski local trivia means that this is representable, so that the Zariski locally, this is a product of some. So locally, so this is a product of some like this. And the same fiber means that so this fiber appears for I equal 1 and 2. So then we have also they have the same class. Anyway, so this last one is the clinical condition, but let's consider a case where the target is just one point. In this case, we know the structure of this quadratic group of stacks. So we write K stack to be K stack over spec C. And of course, it has a bias algebra structure given just by taking the product of the stacks. So in this case, I just omit the map to the target. And also, we also have the natural subspace spanned by varieties, not stacks. Again, I said that the issue about considering Euler characteristic of the stack is that so the Euler characteristic makes sense for varieties. So the Euler characteristic map is defined from here to here, but it cannot be defined on here. This is because for stack the its Euler its cohomology is infinite dimensional in general, and usually it happens that when there are some torus on the stabilizers of stacks. For example, if we consider like BT, when T is like torus, then one may try to define the Euler characteristic like 1 over Euler characteristic of T, but of course the Euler characteristic of the torus is 0, so it does not make sense. But the stack of quadratic group of variety of the stack is, so this is explicitly described in this way. So F is the class of the affine line. The Euler characteristic of affine line makes sense. This is just 1. So if you look at this formula, so this part is the only one which is the abstraction of defining the Euler class. For other part, so the substitution of this one makes sense, and the Euler characteristic of the byte makes sense. So this is only the one which gives the abstraction of defining Euler numbers. And again, so this one appears because of the torus stabilizers of the stacks. Then I'm going to give you the definition of the motoric Hall algebra. So for smooth projective variety X, let recall that we have the modular stack of coherent sheaves over X. So then I define the motoric Hall algebra of X to be the quadratic group of stacks over this modular stack. So this is Q generated by which is symbol. And this is also graded by the Chan characters. That is. Okay, so this modular stack decomposes into the disjoint union over V. So this has Chan character V. And there is a direct sum decomposition of this quadratic group of stacks in terms of the Chan characters. So I get this direct sum decomposition, and this is graded over this monoid. And then there is the algebra structure on this quadratic group of stacks over M. That is called the motoric Hall algebra structure. In order to define it, let mx. So this is a modular stack of exact sequence of coherent sheaves. So in terms of stack, let's send for each scheme S to the groupoid of exact sequences of coherent sheaves, such that each Fi is a coherent sheaf over the product and a flat over S. So this is the modular stack which parameterizes this one, and there are various evaluation maps. So this is this evaluation map is So this is sending this sequence to Fi. So this means that I have this diagram. So this map is sending this exact sequence to the pair of the left and right object, and this map sends this sequence to the middle one. So then roughly speaking, the fiber of this map is something like the X1 of F3 and F1 module some sort of automatism groups. Then given rho I in H of X, I define the product given by pullback and push forward. So the meaning of this pullback and push forward is that I have maps X1, product X2. And the pullback is nothing but just taking the fiber product. And the push forward is nothing but just composition. So then this map is just take the fiber product and then composition with this, the second evaluation map. And in fact, this gives the associative algebra structure on this quadratic group of stacks over X. Yes. And this is called the motivic Hall algebra. So here is a simple example of the product, but so this example is very important because the computation of this product gives the essential part of these constructions. For coherent sheaf, let delta E be the delta function that is the map from spec C to N, which takes point to E. So then for a pair of coherent sheaves, E1, E2, then we can calculate this product this way. So these follows are easy from the definition of the matrix whole product. The basically, so this is because in this product, the fiber of this, the evaluation 1 and the evaluation 2, evaluation 3 is given by this exact sequence. So this exact sequence corresponds to the X1. But you have to take the quotient by some isomorphism groups of the so we want to consider these isomorphism groups of this exact sequence. And because I'm redefining the automatism of E1 and E2, I want to see the automatism groups of this form. And such automatism group is in fact coming from the map from here to here. So such a automatism group is given by the sum of the identity map plus the map for this one. So this is how this product is described. So then the important point is how to define the logarithm of the moduli stack. So let's take amp divisor H. H is amp divisor. And V is element of gamma, so gamma was in H times Q. So then there is a moduli stack of semi-stable sheaves. So that is IoT stack of finite type and with affine stabilizers. So there is a natural open margin. So this open margin gives the element of this motric over algebra. And then using this element, so Joyce defined this element, so-called epsilon function. So this is defined in this way. I take all of the sum of the decomposition V into some part where it has the same reduced Hilbert polynomial. Of course, if there is no strict semi-stable shift, then there is no non-trivial such decomposition. So the epsilon and delta are the same when in the fine case. That is, this is equal if MHV is fine. But we are interested in the case that the moduli space is not fine. And in that case, they are different. So this is formally regarded as a logarithm because so formally it is written in this way. More precisely, if you take some sort of compression of the motif for algebra, then this relationship can be rigorously formulated and make sense. Anyway, so the right hand side can be just u minus and so on. And if you substitute u with this sum of this delta function and compare it both sides, you get this formula. So the surprising result by Joyce is that there is so-called absence of Paul theorem. That is, by taking the logarithm of this moduli stack, that is nothing but this epsilon function. So then this epsilon function is virtually regarded as a variety rather than stack. So then the point is, let this lambda is the subspace, just given this way. So recall that the stack of the quadratic group of stacks is given by like k of variety, 1 over m, 1 over m minus 1, and also this part. And this is the subspace, which is generated by this one without this one. As I said, so this part is the only part which gives obstruction of defining Euler numbers. So in particular, the so-called Euler number map makes sense from here to here, but to the rational number. So that is sending L to 1. And also for the variety, I take the usual Euler number. So this function does not make sense over the quadratic group of stacks, but makes sense over this subspace. So then let's define this subspace of the motif for algebra. So this is defined to be the lambda submodule. So anyway, so this has a module structure over K stack, just given by the product. That is x to n and y goes to just product. And with respect to this natural product, I'm taking its submodule, but submodule over here are generated by Z, where Z is a scheme, not a stack. So because this Euler number makes sense on lambda, and also the Euler number makes sense also for scheme. So this means that the Euler number map makes sense over here. So then the result by Joyce is that if you take the multiplication by a minus 1 with this epsilon h, then this leaves in the regular part. So this means that this, by taking epsilon function, this is almost scheme rather than stack. The reason for taking the a minus 1 is that, so this is the class of the one-dimensional torus. So even in the case of the fine case, the modular stack still has some C-star algorithms. So this C-star algorithm is always appears. We have to take multiplication to remove that. So this means that after taking the logarithm, this says that the modular stack virtually has stabilizer group only has one-dimensional torus. So then by taking the multiplication by L minus 1, we get this regular element. So this is a very deep and difficult theorem. But anyway, so using this theorem, we can define the generalized Donaldson-Thomas invariant. And we have the well-defined Euler number map from this regular part. And similarly, we also have the well-defined variant-weighted Euler characteristic. That is, using the variant function over the stack. So there is the variant function also makes sense over the stack of coherent sheaves. And using this variant function, if there is a map from a scheme, then we can take the pullback of this variant function on Z and then take its integration. So then these maps make sense on all of this regular part of the motif forward algebra. And because this epsilon function is a regular element after multiplication by L minus 1, its chi-weighted Euler characteristic still makes sense as a rational number. So this is the definition of the generalized Donaldson-Thomas invariant. And in fact, if from the construction, it equals to the original DT invariant if the modular space is fine. And in fact, it is also shown by Joyce and Son that this is invariant under deformation of complex structures. So now this is the explanation about the Donaldson-Thomas invariant. Are there any questions? Okay, I'm now going to explain about Donaldson-Thomas and Gromov-Witten correspondence. So let X be a smooth projective curvature seafold. And we discuss three kinds of curve counting theories. The one is Donaldson-Thomas theory, that is counting ideal sheaves, or rank one stable sheaves, and Gromov-Witten theory, that is counting stable maps, and Gopakumar-Vafa theory, counting one-dimensional stable sheaves. And all of them have defined features, and background geometries and technicalities are defined, but they are conjecturally equivalent. And as I already said several times, so this is already established, but this one is much more mysterious. So the rank 1 DT invariant is given in the following way for each integer, and beta is in the second homology class, and by Poincare duality, it is also regarded as element of H4. I define I and beta to be of this DT invariant. So the modular space which defines this one was the Hilbert scheme of point. So Hilbert scheme of curves, which was explained in the previous lecture. And it virtually counts closed subschemes C with dimension C less than or equal to 1, homologous beta, and Euler characteristic N. Then this is integer valued invariant, and then we define the generating sheets in this way. And in the original paper by Moik, Nekasuko, Kokop, and Pande, so they use this genetic sheet to formulate the correspondence with Gromov-Witten invariants. But before that, so there was a computation in the degree 0 case, that is when beta is 0. So in this case, the modular space which defines this invariant is Hilbert scheme of points. So this is not curve counting, but point counting. Then this invariant is well defined, and it virtually counts zero-dimensional closed subschemes in X of length n. So in this case, this invariant is computed by Leonard Fantecchi, and so this is given in this way. And here MQ is the Markov function that is explicitly this is sorry, yeah, this is mistake. This is not sum, but this is a product. And so this is given in this series. And so there is a meaning of this combinatorial of this coefficient. Each coefficient is given by the number of the plane partitions. Anyway, so this is completely well known. And another example is like -1 curve. She is a rational curve that is smooth rational curve that is isomorphic to P1. And also assume that its normal boundary is the direct sum of OC -1. So that is the case of the super rigid rational curve. And in this case, the generating series of rank 1 DT invariants are completely computed. The result is this one. So the first factor is Markov function. This one appears at the counting point, as in the previous slide. If you take with a quotient, and then in particular, if you only consider the degree 1 part, then you see that the series is like this. And in fact, this is a rational function. This is a Lola expansion of this rational function at q equals 0. And in fact, this rational function is invariant under this transformation. So this is if you in fact this one is by taking the multiplication by q squared in the denominator and the numerator, we get this one. So this means that this is a rational function, which is apparently the left-hand side only makes sense as a function near q equals 0. But by writing it in this way, we can take analytic continuation of this function to the point in q in c, but maybe -1. Then it can be analytically continued, and after analytic continuation, we get this symmetry condition. In fact, this rationality is always true. So this is one of the consequences of the so-called wall-crossing formula. For any Calavia seafold and beta in the homology class, second homology class, the quotient series. This quotient series is a rational function of Q that is invariant under this transformation. This was so the previous -1 curve case is the simplest example of this phenomenon. In fact, this phenomena is explained in terms of the derived category. Yes, which I will explain later. Okay, so then go to the Gromfitten side. The Gromfitten theory is more classical animated invariant curves. So yes, in the previous lecture, I also defined the moduli stack of stable maps. A stable map is a map from a projective curve with at worst nodal singularities. So it was looking like this. And the automated group is a finite group. In the Donaldson-Thomas theory, there was no constraint on the singularities, but the curve was always embedded. But in the Gromfitten theory, the curve should have only at worst nodal singularities. But the map is not embedding, but it is just a map, satisfying the stability condition. In fact, there is a doing one-fold moduli stack of stable maps, and it's a good moduli space, and this is a projective scheme. And in fact, there is also a perfect obstruction theory on this moduli stack. But it's not asymmetric, so this is different from the, so this is not written as a weighted Euler characteristic. But anyway, so the moduli stack, this moduli stack admits perfect obstruction theory, and it also has virtual dimension 0 if X is a Calabi-Yau seaport. So in particular, we have the zero-dimensional virtual fundamental class. So I should say this is virtual. And again, so this is Q coefficient because this is a virtual class of the Duini-Manifold stack. But nevertheless, so this is a projective scheme. So then we can define the Gromov-Fit invariant. This is now the rational number. And then we can also consider the genetic series of Gromov-Fit invariant. So then the Donaldson-Thomas Gromov-Fit correspondence is given by, is formulated in this way. And this was proven by Panner-Pixton for many Calabi-Yau seaports, including quintic seaports. And in general, it was recently announced to be proved by John Pardon. So the statement is that there is an equality of the genetic sheets via this variable change. And this variable change makes sense because we know that the left-hand side is, so this is rational function of Q. So the meaning of this equality is that the left-hand side is known to be a rational function. So we can, in fact, regard it as a function over the Q plane. So in the left-hand side, the sheet is the expansion to Q equals 0. But we can artically continue it, the function over here, and then we take its expansion at Q equals -1. Because lambda equals 0 corresponds to Q equals -1. So then by taking the expansion of this function in the left-hand side at Q equals -1, then we get this series of the Gromov-Fit invariant. That is the meaning of the Gromov-Fit and Donaldson-Thomas correspondence. So then I'm going to also explain about other DT type invariant that is called stable pairs. The point is that, so if you look at the DT GW correspondence, this is a quotient series. So it is not convenient to consider the quotient series. So we want to consider the genetic series, not taking the quotient series. And in fact, the stable pair is, so this was considered by Panner and Thomas in order to give geometric meaning of the quotient series. Then by definition, a stable pair in the sense of Panner Thomas is that this is a pair of F and S. So F is a pure one-dimensional sheaf. That is, F is a coherent sheaf whose support is one-dimensional. And the pure means that there is no subsheaf which has zero-dimensional support. And S is a morphism from OX to F, which has at most zero-dimensional cokernel. For example, let's see be a smooth, let's see be a curve. And these are divisor on it. So then we can construct such a pair by taking by constructing this pair. Now F is the sheaf associated with this divisor on curve, and S is a natural map associated with this divisor D. So this is a composition, this is a natural surjection, and this is a natural inclusion. You see that so there is no zero-dimensional subsheaf, and the kernel of S is supported. In fact, kernel S is in fact D. So this is zero-dimensional. So then, similarly to the DT invariant, we can define the so-called PT invariant. For each beta in the second homology group, and also any integer, let P and X beta be the moduli space of stable pairs, F and S, such that the fundamental homology class of F equals to beta and K equal N. Yes, the fundamental homology class of F is that, maybe I will also explain later, but this is the one cycle given by length of eta F and eta 1. So eta is the scheme theoretic point which has dimension 1. Roughly speaking, so this is some weighted support of this sheaf F, and the weight is somehow multiplicity of this sheaf at each generic point of one-dimensional support. And this condition is also equivalent to that the Chern character of F is equal to like 0, 0, beta, and n in H0 plus, H2 plus, H4 plus, H6. So then the Donaldson-Thomas proved that this moduli space of stable pairs is in fact projective scheme. And yes, this is projective scheme. In fact, this is one of the construction of the coherent moduli space for coherent systems given by the Potier. And the observation by Donaldson-Thomas is that this is in fact regarded as moduli space of object in the derived category by associating this pair with this two-term complex. So this says that if you consider some small deformation of this two-term complex in derived category, then this small deformation is again of this form. That is, there's a natural map from Pnx beta to the moduli space of object in here. Then this is open immersion. And this open subscheme of the moduli space of object in here is regarded as moduli space of stable object in direct category. Anyway, so using this observation, so similar to the case of usual sheaves, they construct symmetric perfect obstruction theory. This is projective scheme with symmetric perfect obstruction theory. And therefore, there is a zero-dimensional partial fundamental class. So this is the PT invariant. But then again, similarly to the before, we can define the generating sheet of PT invariant. And this is the so-called the DT PT correspondence that the quotient series, this one, is equal to the genetic sheet of the PT invariant. So that is also a consequence of the so-called wall crossing in derived category. Let's compare two moduli spaces. So this moduli space of rank 1 DT invariant. So this is we call that this is a moduli space of ideal sheaves. But this ideal sheaf is quasi-isomorphic to this two-term complex. This is just by taking regarded IC as a kernel of this map. So in this way, this moduli space is also regarded as the moduli space of such pairs. But this pair is slightly different from the Thomas stable pairs. So if you regard this ideal sheaf as a two-term complex associated with this with some pair, so this pair is that F is now one-dimensional sheaf, but may not be pure. This is because for ideal sheaf, we consider curve, but there might be some point which may or may not lie C. So this means that if there is such a point, then OC may have some zero-dimensional subsheaf. On the other hand, the section S corresponds to this surjection. So this is always surjective. That is, so this in the ideal sheaf case, the target sheaf F must be always structure sheaf of some subscheme. So there are two defines that on F and S. In the DT theory, so this F is not pure, but S is surjective. But in the PT stable pair case, F is pure, but S is not necessarily surjective. So in this case, the modular space is defined from the modular space of PT pairs. We can compare two complexes, two-term complexes associated with rank 1 DT theory and PT theory. For the case of ideal sheaf, in this case, the structure sheaf may not be pure. But if it is not pure, there is some zero-dimensional subsheaf. So if you take Q to be the maximal zero-dimensional subsheaf, so then we get this distinct triangle. So this is because we have this exact sequence of complexes. From this exact sequence of complexes, we get this distinct triangle. On the other hand, if you give a stable pair, then for stable pair, the sheaf F is always pure, but it may have zero-dimensional cokernel. So in this case, instead of this exact sequence, we can take this sequence. Let's take the image of S. Image of S is now structure sheaf of something. So then by taking its cokernel, we get this sequence. But now this first one, so this is the ideal sheaf of this curve C prime. So then in this way, we get this distinct triangle. So let's compare this triangle and this triangle. The middle one is, so this is the ideal sheaf of some subscheme. And this is a stable pair. And IC prime is, so C prime is a subscheme such that its structure sheaf is pure. So this is both of stable pair and ideal sheaf. So this is the point of which appears both in the DT and PT theory. And this is something in Latam. So this is a zero-dimensional sheaf. So by comparing this one, so they are the building blocks of these two theories are the same. So such ideal shifts for the with structure shift is pure, and also zero-dimensional shifts. But the direction of how they are constructed are different. So for this ideal shift, we have these extensions from zero-dimensional shift to this ideal shift, and for stable pair, so this direction is different. So this means that they are constructed by using the different filtrations. So this is regarded as the change of stability conditions, and this is regarded as a different Harder-Nashman filtrations. So this is regarded as different Harder-Nashman filtrations or change of stability conditions. And so let's recall about Brillouin stability conditions. So we have the space of Brillouin stability conditions. So this is the space. Each point corresponds to a stability condition in the derived category. So at each point of sub X, so there is a notion of a semi-stable object in the derived category, and also the moduli stack. It was shown to be outing stack of finite type. So similarly to the previous construction, for each choice of stability conditions, we can define the DT invariant, which counts not necessarily semi-stable shield, but counting sigma semi-stable objects. It is very important to extend the DT theory not only for shield, but also to the object in the derived category. This is because this derived category has more symmetries than usual coherent shields. And this symmetry is important in understanding the property of the genetic series of the usual DT invariant. So then I briefly explain about the work crossing. So we have the space of stability conditions, and there is a so-called wall and chamber structures, such that the each DT invariant, this is constant on each chamber. That is, so in fact, this invariant depends on choice of sigma. And the wall crossing is describing how they depend on sigma. So they are constant on each chamber, but if you cross the wall, so there are some walls. If you cross the wall, then the invariant change. And the difference of this invariant and the wall crossing is described by wall crossing formula. So in general, so this is a combinatorially quite complicated formula. But anyway, so there is such a formula we can apply. So in the setting of DT-PT wall crossing, we can construct stability conditions. So this part is not explicitly written in the literature, but instead before, yes, as I mentioned in the previous lecture, it is in fact difficult to construct stability conditions on threefold. But instead of considering the usual stability conditions, we can consider weak versions of stability conditions. And using weak stability conditions, we can construct sigma I and sigma P, which recovers the DT and PT invariant. And in this case, we have some one wall here. Let's say so this is sub X, maybe weak one. So then we have the by wall crossing, we can delete these two moduli spaces and two invariants. And this, the formula is the one that is the result of the wall crossing formula. So then another application of wall crossing, we have this formula. So in fact, this formula is closely related to the Gopakumar-Vafa formula. So we have the following formula that is the generating series of PT invariant is given by the product of the exponential of this another invariant. So this is the generalized DT invariant, counting semi-stable shifts. So counting, in fact, one-dimensional semi-stable shifts F whose Chan character is of this form. So this is the generalized DT invariant, which is not necessarily integer, but it's a rational number. This last term this is more mysterious, and this is counts certain stable objects E, but with the same Chan character which appeared in the DT or PT invariant. And this is counting stable object, not necessarily shifts, but for some special choice of stability condition, which has some symmetric properties. And this symmetric property gives some symmetry of this invariant itself. So this satisfies these symmetric properties. And in fact, this is also zero when n is sufficiently big. In fact, so this is closely related to the Gopakumar-Vafa formula. So I'll explain later that this one corresponds to the genus zero part, and this one corresponds to the higher genus part. Anyway, so this is also a consequence of the wall crossing. So this is also applied by applying the wall crossing from the stability condition, which corresponds to the PT invariant, and also stability condition, which is not a classical one, but has some asymmetric property. So then now I'm going to discuss more about the Gopakumar-Vafa theory. So far I discussed about PT invariants and Gromfit invariants. However, neither of them are idea of curve counting in the sense that so eventually you want to find some invariant which are in fact in integers and which directly count curves. For the Gromfit invariant, the obvious issue is that it is not integer, it's a rational number, which are not necessarily integers. On the other hand, the PT invariants are in integers, so that is good. But they count not only curves, but also points. This is because, so for example, the typical example of PT pair is that we have this curve and also some divisors. So there are also still contribution of the divisors. And so it is not clear how to get the information of the actual number of the genus G and degree beta curves from the PT invariants. So that's because that the number of degree D rational curves on critical seafood is, so yeah, this was given in my first lecture. And we want to have some sort of this kind of integer valued invariant which recover these numbers. And here is how this number may be derived. So this was the original formula from Gopakumar-Vafa. So the Gopakumar-Vafa written down the left of the genetic sheet of the Gromfit invariants in terms of this formula. So this is motivated by the duality between types N and M theory, which I cannot explain about this. But the point is that so it is always possible to write the left-hand side in terms of this right-hand side, but for some rational number, NG beta G. For example, when G equals 0, this formula is that the genus 0 Gromfit invariant is given by this multiple cover 4 formula. In fact, so for example, so this is only genus 0. 0 beta working. So for genus 0, it is computed from genus 0 Gromfit invariant by the induction of the divisibility of the curve class beta. And the conjecture which was proposed by Gopakumar-Vafa, which was proven by Yone and Parker using symplectic geometry, is that this one is in fact in integer. So in several contexts, the people call this NG beta G as the Gopakumar-Vafa invariant. So when you say about the Gopakumar-Vafa invariant, it depends on choice of the background enumerative geometry. So historically, so this one appeared first, and people call it as Gopakumar-Vafa invariant.
Can you please explain again what is the K?
K. Sorry, K is some integer. Yes, maybe I should say K is some integer, and which divides beta. So beta is the second homologous in G coefficient, and K is integer, maybe positive integer, which divides K. Okay.
But it doesn't have any geometrical meaning. Or
Geometrically, so I don't know how to say. Well, for example, in the case of -1 curve, the growth invariant in the case of -1 curve, so this is just the Kc is 1 over K cube. And K appears as the K times 1 covering of this P1. So I think that this one has to do with the covering of the curve to the target space. So in any case, the graphite invariants are rational numbers because of the multiple cover phenomena. That is, the map from the curve to the threefold is not embedding. So, but yeah, but this is only for the observation in the -1 curve, and I'm not sure whether this is the correct explanation, but and in the higher genus, I think this is more mysterious, I think.
okay.
On the other hand, we can also write the yes, generating sheet of the PT invariant in this way. So this formula is derived just by looking at the PT and GV correspondence, and also expand the PT sheet by following this the GW GV description to the PPT side. So then anyway, so in the PT side, it is also possible to write down in this way. But there is one difference of this description. In this Gopakumar form of the Gromov-Hitten series, it is clear that, of course, NG beta is 0 for G is negative. But it is not clear whether this is 0 for session to big G. But in the PT side, it is not clear whether this is 0 for negative G. A priori, it is always possible to write it in this form, but probably for some negative choice of G. But the point is that on here, so this is not clear whether this is integer, and this is a seldom.
Well, what is the geometrical meaning of negative G?
Yeah, geometric meaning is not clear. So this is just the formal expression. But yes, I will explain that. So this is in fact equivalent to the so-called the chi-independent space phenomena. And so this is still mysterious in geometry, but but anyway, so from this expansion, it is not clear about the geometric meaning. So this is just the formal expansion of this PPT series. And yes, anyway, so of course, this should vanish when G is negative. And in fact, so this vanishing does not hold from the DTGW correspondence. And so under this DTGW correspondence, the vanishing of the negative genus is in fact equivalent to the vanishing of the Gopakumar invariant in the Gromov-Hitten side. possession big G. So this means that under PTT and GW correspondence, it is maybe something like expansion of the two sheets in the different convergence radius, something like that. But in order to show that it really match, we have to show that in fact they are lying in some sort of finite range, so that we have to show either this holds or this hold. So however, so this one is first was proven from symplectic geometry. So this vanishing was proven by Duan, Yonel, Alpsky. So again, from symplectic geometry. This is a completely the statement in algebraic geometry. And so this is quite mysterious that, but nevertheless, we know DT-GW correspondence. And we know this vanishing. So as a consequence, we also know that this is zero. So here we know that this is also zero for negative G. And as a consequence, we know that the two invariants are the same. So yes, so this is somewhat fortunate point for me, because so there's no purely algebraic geometry proof at this moment. But anyway, so we know that we have these invariants. And so anyway, so usually people call this Gopakumar-Vafa invariant and regarded as a fundamental normative invariant of curves. However, the original proposal by Gopakumar-Vafa is that so they want to define these invariants directly through the moduli space of some called D2 branes. So this is now moduli space of stable shifts, one-dimensional stable shifts, not like PT pairs or so on. So they conjecture the existence of these sequence of invariants defined from some cohomology theory of moduli space of D2 branes. So the appearance of the cohomology theory is the different point from the previous story. So far, these are defined through some virtual invariant. So there is no cohomology theory at all. But there should be some moduli space which with some interesting cohomology theory, which in fact match with these invariants. That was what I want to explain in the next lecture. But in the G0 case, that was already appeared in the paper by Katz. And in this case, this is in fact something like the Euler characteristic of this cohomology theory. As I said, so this is cohomology theory, but in the G0 case, so this is Euler characteristic of this cohomology theory. So as I said, so the DT theory is something like Euler characteristic. So in the G0 case, there is some definition using the moduli space of D2 branes. So this is mathematically one interpretation of this one is that we consider moduli space of one-dimensional stable shift F is this Chern character. So this moduli space also appeared in my previous lecture. So the choice of the Chern character is this 00 beta 1. So the choice of this Chern character is just for the conventional reason, because for this choice of Chern character, the moduli space M beta. So this is in fact a fine moduli space. So therefore, we can define the integration of the zero-dimensional partial class. So Sheldon Katz defined the genus zero Gopakumar-Vafa invariant in this way. But this was before the genus DT invariant was constructed. So this is following from the original construction of Richard Thomas. So if this one is not one, there was no way to define the DT invariant. But after that, there was a work by Joyce and Son defining generalized DT invariant. So then instead of this one, we can also define the generalized DT invariant, where this is chi. Let's recall that this also appeared in my paper about this. So PT equal exponential of n and L. So this part is this the generalized DT invariant part. And this is why I said that this corresponds to the genus zero tail part. Anyway, so yes, we can also consider this one. But now this is generalized DT invariant. So this is just a rational number. But instead, we can define the N0 beta chi. So this is the genus zero analog of the Vafa invariant, but not take one, but for some other chi. This is defined using this multiple cover formula. So this is very similar to the multiple cover formula of the genus zero Vafa invariant, but the difference is that this power of not 3, but 2. But anyway, we can define a priori, so this is a rational number. But using this multiple cover formula, we can define this number. So this number is also called BPS number. As I said, so this is, so in fact, I explained about this formula that, so the formula was that P, the generating series of PT invariant. This is the exponential of T beta, and also the generating series of other invariants. So this is, this is the consequence of the Wall-Cauchy formula. And but this part is just the general DT invariant. And just substituting this formula of this multiple cover formula. So this is N beta chi. And comparing with the Gopakumar-Vafa formula, then one can see that this N0 beta chi is independent of chi, if and only if we have the vanishing of the negative genus of P. So as I said, so this one is not to be true because of the vanishing of the Gopakumar-Vafa invariant from the Gromov-Fit invariant, and also the Gromov-Fit PT correspondence. And we know that this is true, but again, so this is, we know that this is true from the consequence of the Gromov-Fit PT and also the vanishing from the symbolic geometry side. But in algebraic geometry, so this vanishing is equivalent to this chi-independence phenomena. So in fact, so the from the physics point of view, there's no reason why we should take chi for 1. So there should be invariant for any choice of chi. And the resulting invariant should be independent of chi. So this is the suggesting of this one. So this choice of chi should not be relevant in the theory. But mathematically, this is quite surprising phenomena. And so in many cases, so we know that this is true by computation, and but so far there's no conceptual understanding. But there's, I will also explain later next time that there are some decent works by Morik Shen and also the Kinjo Koseki, which gives some conceptual understanding of this phenomena, not even in the genus there, but also in the higher genus. And but in general, so this is still not know how to prove it from purely algebraic geometry. But on the other hand, using symplectic geometry and also GWPT correspondence, we know that this is true. So the consequence, we know that this is also true. So by putting everything together, so we have that in genus zero, we have a complete picture. That is, we know that every so-called Gopakumar-Vafa invariants are the same. That is, we also have the chi-independence, and they also same with the genus, we also have it coincide with the Gopakumar-Vafa invariants defined from Gromfitten or PT invariant. As a consequence, we have this so-called multiple cover formula. So this is the point of this one is that this is counting stable maps. And for here, so this is I employ the definition by cut. So this is counting stable sheaves. So we know that this is true, but so our purpose is to define the higher genus Gopakumar-Vafa invariant using the modular space of stable sheaves. In higher genus, Gopakumar-Vafa's proposal is to consider the some de-algebra action on the modular space of stable sheaves. So far there have been several mathematical approaches for that. Hoson and Saito Takashi used the intersection cohomology, and Kim Lee used the some sort of associated grid of some vanishing cycle complex called DT Papa sheaf. But in my paper with Taweshima Week, we showed that there are previous constructions of counterexamples to the conjectural equality of the PT or conflict invariants. And instead, we have some another proposal use some sort of perverse filtrations. And in fact, there are also Saito Takashi, Kim definitions for counterexamples to this. So far, our definition is the only one which still survives. So there's no counterexample not yet found. So anyway, so the next lecture I explain about this definition using power shields, and then formulate this one. And maybe probably we'll also discuss about some open problem or also chi-independence phenomena. Okay, so I stop here. Thank you very much.